Hi everyone and welcome back. This is a problem from the Russian Olympiad in 1996. Pause video if you want to give this problem a go, and when you're ready, we'll go through the solution. We can begin this problem by first considering if k is even, so we can write that as 2m for some integer m, and then this equation can be written as x to the m squared plus y to the m squared is 3 to the n. We can see quite clearly that n must be bigger than 1, and given that we know x and y are both coprime, then we know that if 3 were to divide x, since it already divides 3 to the n, it would therefore divide y to the k. Or in other words, we would be saying here that 3 divides x and y, which contradicts our coprime condition. And so we must conclude that 3 does not divide x or y. Now, all this to say that x and y will both be either 1 or 2 mod 3, and x squared and y squared will just be 1 mod 3. But then this equation tells us that we have 1 plus 1 is congruent to 0 mod 3. Or in other words, 2 is congruent to 0, which is of course nonsense. And so we can conclude that k must be odd. And since we know k is odd, we can factorize x to the k plus y to the k as x plus y multiplied by x to the k minus 1 minus x to the k minus 2 times y, and this will continue upwards until we arrive at x to the y k minus 2 plus y to the k minus 1. And for simplicity, I'll just refer to this polynomial as p, and since x to the k plus y to the k is a power of 3, then it follows that x plus y must be a power of 3, and the polynomial p must also be some power of 3, and both of these are going to be bigger than 1, so we can say that both a and b are greater than or equal to 1. And we can rewrite y as 3 to the a minus x, and if we sub this into the polynomial p, we can see that this will equal x to the k minus 1 minus x to the k minus 2 times 3 to the a minus x, and upwards until we arrive at 3 to the a minus x to the k minus 1. And what we'll notice is that we have x to the k minus 1 appearing k times, and then the other terms will just be some power of 3 to the a times some other polynomial q. But we already know that 3 divides p, and it definitely divides 3 to the a, so therefore it must also divide k x to the k minus 1. But we already established earlier that 3 cannot divide x, in which case we must say that 3 divides k, or in other words, k is equal to 3. So now we're looking at solving the equation x cubed plus y cubed is 3 to the power of n. We can factorize this as x plus y times x squared minus xy plus y squared. And just like before, we can write x plus y as some power of 3, and x squared minus xy plus y squared as another power of 3. And just like earlier, we know that a and b must both be bigger than 1. Now notice from the second equation, we can write this as x plus y all squared minus 3xy is 3 to the power of b, or in other words, this is 3 to the power of 2a minus 3xy is 3 to the power of b. And we can divide each of these by 3, so we can say 3 to the 2a minus 1 minus xy is 3 to the power of b minus 1. And since we know that 3 does not divide xy, then we must say that one of these must equal 1, in which case we have either 2a minus 1 is equal to 0, or b minus 1 is equal to 0. In the first case, there's no solution, and in the second case, we have b equal to 1. And so we're solving the equation x squared minus xy plus y squared is equal to 3, and we can see that xy plus 3 must be bigger than 0, in which case we can say that xy is bigger than minus 3. We can also rearrange the top equation to be x minus y all squared plus xy is equal to 3, and so we know 3 take away xy is bigger than 0, or in other words, xy is smaller than 3. And from earlier, we know that this is bigger than minus 3, in which case we have the only possibility to check for xy to be 2, 1, 0, minus 1, or minus 2. It's not too difficult to check that 0 is impossible, as is 1, minus 1, and minus 2, and when xy equals 2, we have two possibilities here. Either x is 1 and y is 2, or x is 2 and y is 1. And so we're done.